Welcome to this session on model diagnosis and advanced regression techniques. In this lecture, we will begin by understanding the core assumptions of linear regression. We will then explore diagnostic tools used to validate model performance and identify potential problems. After that, we will move to advanced regression methods, including logistic regression, ridge regression, lasso, and elastic net. Finally, we will look at how to implement these concepts in R. Let's begin.
The first assumption of linear regression is linearity. This means that the relationship between the predictors and the response variable must be linear. We examine this using scatter plots, residual plots, or component plus residual plots. If a noticeable curve appears, the assumption is violated. Nonlinearity can lead to biased estimates and poor predictive accuracy. The next assumption is independence of residuals. Residuals should not be correlated with each other. This is especially important when dealing with time series or sequential data. The Durbin-Watson test is commonly used to detect autocorrelation. If residuals are dependent, standard errors become unreliable, and statistical tests may not be valid.
The third assumption is homoscedasticity, which means the residuals should have constant variance across fitted values. When this assumption is violated, we observe patterns such as funnel shapes or widening spreads in the residuals. This condition is known as heteroscedasticity. It affects confidence intervals and hypothesis testing. Residual versus fitted plots are typically used to diagnose this issue. The next assumption is that residuals should be approximately normally distributed. This is assessed using QQ plots or histograms of residuals. While small deviations from normality are acceptable, severe skewness or outliers can impact inference, particularly p-values and confidence intervals. Normality is essential for reliable statistical conclusions.
Once a regression model is fitted, several diagnostic plots help evaluate its validity. The residual versus fitted plot checks linearity and homoscedasticity. The QQ plot checks normality. The scale location plot helps identify variance issues. A residual histogram gives additional insights into the distribution. Together, these plots highlight whether assumptions hold or if model adjustments are required. D. Multicollinearity occurs when independent variables are highly correlated with one another. This leads to unstable coefficient estimates and inflated standard errors. Variance inflation factor, or VIF, is used to quantify multicollinearity. A VIF above 5 indicates moderate multicollinearity, while values above 10 signal serious problems. In such cases, we may remove predictors, combine them, or use regularization techniques.
Influential observations are data points that can disproportionately affect the model. Cook's distance is a diagnostic measure used to identify such points. Large spikes in the Cook's distance plot indicate potential influence. It is important to examine these observations to determine whether they represent data entry errors, special cases, or genuine extreme behavior. Handling influential points appropriately improves model stability.
Logistic regression is used when the dependent variable is binary. Instead of predicting a continuous outcome, it estimates the probability of an event occurring. It uses the log odds transformation, and predictions range between 0 and 1. Logistic regression is widely used in applications such as customer churn prediction, loan approval, medical diagnosis, and classification tasks. When dealing with many predictors or multicollinearity, regularization becomes useful. Ridge regression shrinks coefficients but does not eliminate any of them. Lasso regression performs both shrinkage and variable selection by forcing some coefficients to exactly 0. Elastic net is a hybrid method that combines both ridge and lasso. These techniques improve model generalization and stability, especially with high-dimensional data.
When the relationship between predictors and the outcome is nonlinear, polynomial regression or spline models can capture curved patterns. Polynomial terms allow the regression line to bend, while splines create flexible, piecewise curves. These methods increase model accuracy when linearity is violated. However, they should be used carefully to avoid overfitting. All the concepts discussed in this session can be implemented easily in R. Linear regression uses the LM function, while logistic regression uses GLM. The variance inflation factor can be computed using the CAR package. Regularization methods, such as ridge, lasso, and elastic net, can be implemented using the GLMNet package. Before trusting any regression results, always perform model diagnostics. This ensures that your results are reliable and mean. Continue watching Part 3 for actual working on R.
Always share the videos of Dr. Sachdeva to your friends who are interested in data analysis.